Hello everyone, my name is Laszlo Kozma and I'm presenting a joint work with Benjamin Berendson and Michael Oppler about optimization with pattern avoiding input. So here are a number of optimization problems which seem to be at first completely unrelated to each other. The first is the Euclidean traveling salesman problem. So we are given n points, let's say in a unit box, and we have to connect them by the shortest possible tour. And we can consider also other geometric problems on point sets, the minimum spanning tree, Steiner tree, or certain Manhattan network problems. Here is a different problem. We are given a sequence of searches and we have to implement them in a binary search tree. So we search down normally from the root, but after that we are allowed to rotate the tree such as to prepare for the next search. And we want to do it as efficiently as possible. And the last problem is the K-server problem on the line. So we are given K servers in this illustration. Text is on a line interval, and requests arrive one after the other, and we have to move one of the servers to the request. And we want to minimize the total movement of servers. So what is common in all three of these problems as we study them is that we restrict the input by avoiding permutation patterns. So let me define this concept through an example. So here is a sequence of numbers 8, 5, 1, 7 and so on. And we say that this sequence contains a pattern, in this case 1, 3, 4, 2, because there is a subsequence which I highlighted here in red, 1, 7, 9, 6, which is order isomorphic to the pattern. So 1, 7, 9, 6 has the same ordering as 1, 3, 4, 2. The same text, for example, avoids 1, 2, 3, 4 because there are no 4 elements in this sequence which would be in increasing order. And it's very intuitive to visualize this as point sets in the plane. We can put the sequence on the x-axis and the values on the y-axis, and as illustrated here, this sequence contains this 1, 3, 4, 2, meaning that this point set representing the sequence has 4 points in the same relative position as 1, 3, 4, 2. And as we said, this sequence avoids 1, 2, 3, 4. So it's obvious that we can extend this concept of pattern containment or avoidance also to planar point sets. Okay, so our main result, stated informally, is that the complexity of these optimization problems that I mentioned is reduced whenever the input avoids some pattern. And this pattern can be arbitrary, and it's even unknown essentially to the algorithm, so the pattern avoidance is only used in the analysis. So our analysis will apply to general purpose algorithms for these optimization problems. And here are our results. So for Euclidean TSP, we show that the cost, meaning the length of the tour, reduces from square root n to log n asymptotically if the input avoids some pattern. In the case of binary search trees, the total cost of searches reduces from n log n to order n. If you will, the amortized cost of searches reduces from logarithmic to constant under pattern avoidance. For K-server, the reduction is from a total cost that is linear in n to some sublinear n to the epsilon, where this epsilon will depend both on the pattern and the number of servers k. So this quick statement of results hides some dependence on the pattern in the big O notation, and for K-server, the number of servers has to be much larger than the pattern. So this is just a small observation. Okay, so I will talk mostly about the second of the results, dynamic binary search trees. So here is the setting. We start with some tree on storing n keys, and we have a search sequence of n searches, and we have to perform all these searches in the usual way For example, if we search for 6, we search down from the root along the search path to 6. So for each of these elements of the sequence, we search down for that element, and then we are allowed to rearrange the tree by rotation. So we move a pointer around and we may do rotations in the tree. Not just on the search path, but we can also wander away from the search path. But we have to mark which nodes we touched in the tree, and that will be our cost. So the cost is the total search cost plus the number of nodes that we touched when we were rearranging the tree. Okay, so there are two ways to look at this problem. One is in an offline setting where we are given this sequence and we want to design the best way to serve the sequence, which means coming up with an initial tree and a sequence of rotations. And it is known that in general the cost of this will be n log n. This comes from a basic information theory, but for some structured sequences we may be able to do better. And I should mention that the complexity of computing this optimum is wide open, even approximately, so it's not known to be NP-hard or polynomial time computable. And then there is an online view of the problem where we receive the searches one after the other and we have to immediately serve them in a dynamic tree, for example, in this display tree data structure. And of course, the big question is there an online strategy which is constant competitive with the offline optimum? So this is the dynamic optimality conjecture by Slater and Tarjan. Okay, so we will mostly look at the offline problem. So we want to design the best way to serve the sequence x1 to xn. And as I said, we know that n log n is a lower bound for most sequences, but this comes basically from the fact that there are n factorial input permutations, and we take the logarithm of that. But what if the sequence avoids some pattern? Well, then we know that there are only single exponentially many such input permutations. So this is it was a famous conjecture, the Stanley-Wilf conjecture, which was proven by Marcus and Tardos in 2004. So we know that because there are only single exponentially many such inputs, information theory would allow a linear optimum. So it may be possible to serve such sequences in linear time. And the motivating question is that it may even be possible to sort such sequences in linear time. Okay, so this is our goal, and I should mention that this is known to be doable in special cases when the pattern is a very particular small pattern. So for example, if the pattern is 2, 1, then the input is sorted. That is obvious. But a few other small cases are also known. So our goal is to prove this for an arbitrary pattern generalizing these results. Okay, and something is known in general, so it's known that this optimum is almost linear. So it's this n times this function which depends on this alpha n, the inverse Ackermann function. So it's not quite linear, but it's almost linear. So these were shown in recent years. And I should mention that these results hold for online algorithms. But what is our result? We close this gap. We show a linear bound for the offline optimum. Okay, and we leave it as an open question to show a linear bound also for some online algorithm like display tree, which must be true if the dynamic optimality conjecture holds. Okay, so how do we prove this result? We combine two broad techniques. One is the geometric view of binary search trees, and the other is this recent concept of twin width and merge sequences. So first, the geometric view of binary search trees, it allows us to view a sequence of operations in a binary search tree as a point set. So first we plot the input, the sequence of searches, and then we can plot the nodes that are touched in the binary search tree at any time. So these different colored points mark the nodes which are touched during each search and rearrangement of the tree. So we find a superset of our input point set. And it turns out that there is an exact characterization of which point sets describe a valid binary search tree execution, and the condition is that there should be no empty rectangles, meaning that there should be no two points forming the corners of a rectangle which has no other points inside. So for example, this figure on the right actually has an empty rectangle which I marked with red, but if we add this other point in the corner, then it's no longer empty, and it can be checked easily that then this point set is valid, so it describes a binary search tree execution. So the goal is to do this with as few points as possible, so finding the smallest superset of points with no empty rectangles is the same as finding a valid binary search tree execution. So the cost will be the number of points in this superset. Okay, the second tool is twin width and merge sequences. So here we use a result which says that if X, a point set or a permutation, avoids a pattern pi, then X has twin width some function of pi, which is the same as saying that X has a merge sequence of width, this C of pi. So this is a result by Guillemot and Marx from 10 years ago, and this C of pi is the so-called Füredi-Hoynal constant of pi. It's a quantity which depends on the pattern pi. And what is a merge sequence of X? Well, we start with this point set X, and we view them as tiny rectangles. And in each step, we take two rectangles and merge them. So we remove them and add the bounding box of the two rectangles. So, for example, we may take these two rectangles and combine them into this larger rectangle. Then this, then this, then this. So the rectangles can also overlap. And after n-1 steps, we end up with a single rectangle. Okay, so there are many different possible ways to merge these rectangles into a single rectangle, and the width d of this merge sequence means that during the sequence no rectangle sees more than d other rectangles, and seeing another rectangle means to overlap with it horizontally or vertically. So if this width is small, it means that the rectangles can overlap only with few other rectangles horizontally or vertically. Okay, and just to recap this statement, so if X avoids some pattern, then there is a merge sequence of small width. Okay, and now we use this merge sequence to guide the construction of the binary search tree execution in the geometric view that I mentioned. So we follow this merge sequence and we maintain the invariant that inside each rectangle we already have a solution. Okay, this is true initially because each rectangle is a single point which is valid, and we just have to take care that when we merge two rectangles, we establish the invariant. So we have to add some points then, and because of the low width, we can show that we only add a limited number of points during each merge. And then by the invariant, in the end, we will have a single rectangle, so it will contain a valid binary search tree execution. Okay, and the cost will be n times this Füredi-Hoynal constant squared. And I should mention that this takes n log n time to compute, but that is not important for us. Our measure is the complexity of the point set that we construct. Okay, just very briefly about the traveling salesman problem. So here we know that given n points in a unit box, the worst case cost could be square root n, and this is tight asymptotically. But here is a motivating example. If the point set avoids 1, 2, the pattern 1, 2, it means that they form a monotone chain, so clearly we can connect them in a constant length tour. More generally, if the point set avoids 1, 2, up to k, then we have an order k a tour of this point set. So our result is a more general claim. If the point set avoids any pattern pi, then the cost is logarithmic, order log n. And we show that this is tight for almost all patterns pi, so in some sense these monotone patterns are the only exceptions. Okay, how do we show this? Again, we use the same merge sequence to guide the construction of a minimum spanning tree, which in the end we can transform to a TSP tour. So as we do these merges, we connect the points to form a minimum spanning tree, and we end up with an MST of the entire point set. But observe that this is sensitive to how large the rectangles are. So we don't want the rectangles to be very large because then the spanning tree will be long. So we have to modify this merge sequence, and we introduce a distance balanced merge sequence, which may be of independent interest, where we make sure that the kth rectangle, the kth created rectangle, has about average height and width. So the width and height are this constant c of pi divided by n minus k. And then if we add up all these, we end up with a harmonic sum, so the total cost is order log n. Okay, to summarize, so for Euclidean TSP, we show the total cost to be this constant Füredi-Hainal constant times log n. For binary search trees, the cost is n times the square of this constant. For k-server, it's a more complicated expression, but in some regime where k is larger than this constant, we get sublinear cost. And the results are essentially tight up to the dependence on the pattern pi. So in some cases we can say something more about it, but in general the dependence on n and k is tight. And for special classes of patterns we can prove a stronger bounds. Okay, to summarize, we show that pattern avoidance reduces the complexity across a variety of optimization problems. And we show this by a new type of use of twin width for constructing low complexity solutions. And there could be an analogy maybe here with the graph algorithms, where the avoidance of an arbitrary minor leads to separators and low complexity solutions. Here we look at the sequential input, and the avoidance of a pattern leads to low complexity solutions. And an open question is to find other examples where pattern avoidance may help. For our binary search tree result, an open question is to match the result. Recall that our result was for offline cost, so it would be nice to match this by an online algorithm such as Splay or the so-called greedy binary search tree. And this is a new barrier to dynamic optimality, because if there is a constant competitive online algorithm, then now we know that it has to have this pattern avoiding properties, so it has to match the optimum. And another question which we leave open is whether we can actually sort a pattern avoiding input in linear time. But this has been solved after our result by my co-author Michael Oppler, so this is no longer open. So that's all. Thank you for your attention.